All right, guys. Good morning. Let's get started. So this session and on Friday we're gonna talk about validation and how we're gonna use validation in order to better reduce our out of sample error. And starting from next week, we're gonna have SPNs. All right. I'm not sure if you heard the news, but so Jeffrey Hinton and his two collaborators, Yoshua Bengio and Jan LeCun, won the Turing Award today. So it's a big deal actually. So Turing Award is sort of a Nobel Prize for computer science. All right. Okay, let's get started. So let's talk about validation set. What exactly is a validation set? So say you have your big data set, which contains the distribution of all x's. I'll show it with capital X, right? You have many points. Think about it as the marble, the jar of marble that we talked about before. And you take a sample smaller, and that was your D, right? Out of this D, you could have your in-sample error. And the rest, the big X, was your out-of-sample error, your test cases. So this was your training case, right? So what if inside this sampling, you allocate some portion of that, like this portion. So say you have n samples, you allocate k of those, right, to use as a test case for your training data, for your D, right? So instead of using these, use a portion of the sample you had, which was n, use k of those as test case while you are training your model, right? Still, using this doesn't affect changing any of the test error that you had on the bigger X. So the rest that remains for you to train on is going to be n minus k, right? So we call this k a validation set. It acts as sort of a test set for your training data, right? And today we're going to talk about how we're going to use this validation set in order to come up with better hypotheses, right? I'm sure you've seen validation error and training error while you're training your models using TensorFlow or Caffe or other thing. So this is a very useful notion in training a model in machine learning. All right, so let's talk about training error. So in sample error of G, the hypothesis G. So we would just have to make a pointwise calculation of error. So small e, pointwise error, one by one, and over all of them. That's why we normalize them to n to come up with the in-sample error of your final hypothesis, your candidate G. I'm not sure if you can read this. Let me just remove that. So, as before, we defined test error, out of sample error of your candidate G as the expected value of this pointwise error. This is for the classification case. For the regression case, you would have used squared error, right? All right, so now the problem is how we're going to estimate the out of sample error for G from training data. It's very good, it's very plausible if you could find a way to estimate what's going to be a test error, out of sample error, while we are training a model. And that's exactly why we use the validation set, right? So you have your data set D, contains all your points, x1, y1, and they're coming independently with px function, so it's probability. And they mimic, so y of I is going to be f of x of I And the way we partition the training data, D, is by allocating K of those. By allocating K of those K samples, and we refer them to validation set, so D val, and the remaining, so you had like this and this, that was your D, you allocate K of those for D val, and the rest would be N minus K for D train, right? This is the way you partition your training data. And then while you're training, you just pass the D train instead of the big D, right? So now you have a reduced number of samples, right? And most of the cases, this G, actually here as well, becomes something like this, G minus. You show it this way. It shows that the G was learned from a smaller set of samples in D. Just to showcase that it was that training data had some validation inside, but that's not a big deal. Okay. Yeah, just like all these. So these G's also have this this bar minus bar there. All right. So we can define the eval of G just like what we did with the bigger D at first, as a summation of all x's and y's inside the validation set, pointwise checking error, your G and your real value, class, in the case of binary classification. And then you will have to divide them by number of K's, right? Because we have K samples. So now we're interested in finding whether this holds, right? So the validation error, we hope that it's going to be somewhat close to out of sample error of the G bar, thus the final out of sample error of the G itself. And also we can infer this knowledge that validation error is treated as unbiased estimate, right? So it's unbiased because we didn't change anything in our data set. So this is a very good estimate. Val. Let's say eval. Because our samples are coming from an IID distribution, right? So they are independent. That's why using a validation error is going to be a very beneficial and unbiased estimate in order to estimate the final out of sample error while we are training. Okay? Okay, so let's see the properties of having a validation set. First of all, number one is the expected value of dm is going to be the expected value of dm of validation error of G. We hope that it's going to be close to out of sample error. So we have to provide the proof later on. Right? Again, just like I mentioned, we have this G minus bar there because some points are taken out of D, right? That's why this is, instead of this, we show it like this, most of the cases. But that's just a notion, it's not a big deal. All right, number two. We hope that we want to make sure to provide the proof that the variance of validation error is going to be 1k sigma 2, right? So this is the variance. If you recall, previously we had this formula, the variance of pointwise error for g minus bar x and y. Thus, we can put this in place. So the expected value of x, your x in your data, of the differences between the pointwise error and Eout of g squared, right? This is the second property. And the third one that talks about your confidence level. So with probability greater than 1 minus delta, so say that your delta was 0, 1, or 5, thus this become with more than 95% confidence level. We're going to say that this inequality, which is an expansion of your Hefting's inequality with union bound, will hold. Like the outer sample error of g minus will be always smaller or equal than in sample error of g plus the square root of 1 over 2k log 2 divided by delta. So now we need to understand, after we provided the proof, we need to understand how we're going to select this k, right, out of our sampling data, out of our training data. Okay, so let's start proving number 1. So that was our original D. We divided to D train and D val, right? And then we estimate the error of val as validation error of G minus. So estimating each of those points, the summing of each of points divided by their number of samples in that D val. And then we're going to say, let me just close this again, what happened? Okay, the expected value of D val is going to be the eval, or the, the expected value D val of validation error would be equal to, so instead of this, we're going to put that in place, 1k, and the summation of each of those pointwise error divided by their number of samples. And we carry on the next slide. Okay, so now let's carry on. Now we can bring the 1 over k and summation out of the expected value here, and what left is the pointwise error of the g minus bar x, our estimate, and the real labels, right, yn. We can expand this. If eval is equal to the expected value of x from 1 up to k, right, because we had k samples in deval, and this would be equal to, because we have an unbiased estimate, and these are independent, so we can treat it as sort of an xn, right, a random variable. That's why it's going to become 1 over k summation of all the n's from 1 to k and expected value xn and a pointwise error, right? So actually the first step shows the linearity of the expectation. And secondly, this shows that, so linearity. Secondly, this shows that x1 up to xn only depends on, I'm sorry, x1 up to xk only depends on xn. Right? And we knew before that this is equal to out of sample error itself. Right? So using a validation set taken out of your samples of your training data could actually somewhat mimic your out of sample error. So it's very good for us to use that. All right? So let's talk about this second property. Okay. So we want to calculate the variance of validation error, right? So the variance of eval, again, the validation error would become this. Put it in place. K samples, you want to sum up all the errors pointwise and divide it to k, and then this would be equal to 1 over k2 of variance. So if you recall the random variables, that was a property of a random variable property to define the variance this way. It's going to be 1 over k squared var of the summation of points from 1 to k, your e's, and those represents, of course, your en. Since each of your e's from e1 up to ek are independent, right? Each with the variance of en sigma 2, right? And we talked about this LHS how we're going to use this LHS with respect to a random one. So it's coming from a random distribution as well, by keeping the rows and columns in place. So we make sure in 2D this tree. For instance, in 2D we preserve, if you recall, I was exemplifying a chessboard, like when you have some rocks, you want to make sure they don't threaten each other. So 4 would become something like this, right? You make sure each row and each column has complete random occurrence here, and you keep track of them. All right. So LHS is having the 1/k2 variance of sigma ends from 1 up to k of En, and this becomes sigma 2 over k, right? So that's the proof for our second property for validation set. Okay, let's talk about the third one. So G minus bar, the function is a fixed hypothesis with respect to our validation data, right? Because changing that okay. And validation error was computed as we saw already, so the En over the sample mean, and we knew that out of sample error, the real test error, was the expected value of En, right? So that would be the mean of the whole distribution of big S X, right? The whole bar of marbles, or the overall data set outside. So let's use Hefting's inequality and the union bound to have an upper bound for the differences between out of sample error and in sample error in this case. Okay, so if you recall, we had the Hefting's inequality. So now if we interchange validation error with the out of sample error here, so using Hefting's inequality, we can say the probability of the differences between these two errors is within epsilon, right? The probability of being this value within epsilon is going to be smaller and equal to 2 minus exponential, so multiply an exponential of minus 2k sigma 2, right? That was what we knew. And we would call this delta there. So with a confidence level of 1 minus delta, we can say this inequality holds. So out of sample error is going to be smaller than validation error plus the root square of 1 over 2k log 2 delta. Now we have an upper bound. So now we can play around with, defining how we're going to limit our out of sample error using a validation set, right? So now the only parameter left here is that k, and we have to decide it while we do training, right? In practice, how we're going to come up with the right k. Also, this also applies to non-binary cases, but the case become more complex, so we don't discuss it here. You can use VC dimension or have things inequality, but it becomes more complex in this case. So now the question is, how are we going to select that parameter k? All right. So, in order for our validation error of G minus to be as close as possible to the real out of sample error, right, we need to select a large k. It makes sense, right? So that was your D you were using to train your model, that was your samples, and that was your all x's outside, right? This would come from there. And you allocated k of those for val and n minus kl to train. So in order to be these two to super close to each other, you need to have a large k, right? So the out of sample error of G minus, right, those reduced set here, the hypothesis that was trained on a reduced set of n minus k, in order that to be equal to out of sample error, it needs n minus k as well. So this refers to this data. And in practice, people have found that using a k sort of equal to n divided by 5 is a reasonable choice to have the best of two worlds, right? K and n minus k. So this is one of the rule of thumbs people use in practice. So now we know how we're going to select k, right? The other question is, within our hypothesis H, the set of all hypotheses, H1 up to Hm, how are we going to exploit this val while we're training, and how do we come up with the best of either of them? So how are we going to select the best M star, right? H of M star. And that's what is referred to as model selection. Okay. So the problem here is given a data set D, select the best model from your hypothesis set. So pick one of those, H1 up to HM. So each of these H could contain a set for themselves, right? We are talking about the generalization case. They have their own small H's inside, right? Which one we pick? So example would be HI could be the class of polynomials of a given degree, right? Each of them could be all right. So the idea is to find a way to use the validation set or dval to select the best model, right? So we're going to see it in a few steps, and they're pretty easy and intuitive. Okay, so you see validation set can be used to estimate out of sample error for more than one model, right? So step one, we're going to train each of those hypotheses, right? Or class of hypotheses within certain polynomial degree on training data, right? To output a model G minus bar n in that class, right? So first we start by training using each of those H's, H1 up to HM. Now after we train those, we need to evaluate those, each model on the validation set. Instead of evaluating them on the test set, after we train them, we're going to use validation set to evaluate their validation error, right? So step two would be using the val, compute the validation error of G minus M for each of those M's, right? So this is training on dtrain, evaluating on dval. So we knew that by the first property, evaluating those GMs, G minus bar M's, will give us the out of sample error, right, for each of those HMs. So now after evaluating number two, we have a bunch of out of sample errors. We have some errors here. So at this point, it's a pretty straightforward task. You just have to pick the one with the lowest error, right? It makes sense. So pick the one lowest one. All right. Now finally, after we pick the best hypothesis, now we're going to come back and train on the complete data set, right? Which with that hypothesis M, the best one, the H of M star. And output the resulting hypothesis G star M, right? Now that we use the validation set in order to pick up the best hypothesis, now we don't need to downsample, lower our training data. We can train it on all of the data because we knew that this is the best hypothesis that's working given our data. And this will generate the best candidate that we could have achieved with our learning method, learning algorithm, and our hypothesis. All right? So the diagram goes as this. You have several H's from 1 to M. For each of them, you're going to train on your training error, on your training data, detrain, and then each of them will output one hypothesis of their own, G minus 1, G minus 2, G minus 3, G minus M, and then you use the validation set in order to bring the validation error here. And through this validation error, we pick the best one. We come back and we train it on the complete set. And this will output G star M. So now the final question would be, how are we going to estimate the error, right, involved with that G star M now? Can we find a way to have an analysis, to have a bound on the error involved with this method, like the way we generated G star M? Right? So estimating the real out of sample error. So by now we saw that we have computed the validation error of G minus bar M. So that was the best case that represented our HM, right? So ideally, the validation error of G minus bar M star would be sort of equal to the real out of sample error, right? The real out of sample error of the smaller set. And also ideally it would be almost equal to the actual out of sample error So we saw that also the expected value of the val of validation error of GM is going to be equal to the out of sample error of the smaller set, the hypothesis that was trained on the smaller set. For each of those M's, right? We already saw that. So now the question is, so here's the question. Is out of sample error equal to the expected value of the the validation error of GM? Does anyone have any idea how to answer this question? Do you think this holds? What do you think, guys, the answer is? Yes or no?
Yes.
Why yes?
Should be.
Should be. Do we have any no's here? All right. Remember that M star is not fixed, right? It could change depending on the validation set that we pick. If it was fixed, your answer was okay. But sometimes, depending on the way we select the validation set, so here could be validation set, we might select it here, we might select it there, right? Or we play around iteratively. In next session, we're going to see that cross-validation methods. So we're going to keep changing those Ks, right? So since they are not fixed and depend on dval, so M star is equal to M star of dval, right? All right, so let G be the set of G, all the smallest set of G's, right? So these G's have been trained on a smaller set of training data. So G1 up to GM. So G is computed using the train only, and G is fixed with respect to dval. Say in one case you had a fixed case that was only this, the train dval. That was this. G minus bar M star is a subset, is included in G, right? And it's selected using dval, because the way we mentioned those steps, how we're going to use validation set in order to come up with the GM star, right? So the validation error of the G minus bar M star, right, depends on the way those K's, right? 1 over K, summation of all n's up to K, the pointwise error of the G minus M star xn, and m, right? And this itself, finally, is equal to the out of sample error of gm star, expected value of the pointwise errors. So we will have the probability of the validation error and out of sample error. So using the Hofstad's inequality, now we can expand it to find the differences between the validation error and out of sample error in this case, instead of the first D or D train, right? Now this is the third expansion of the Hofstad's inequality. And finally, we can say with probability of above 1 minus delta, which was your confidence level. So with this confidence level, we can say the out of sample error of G minus M star is always smaller or equal than the validation error plus an order that depends on your M and your K, right? So this was the parameter that would hold us not to have that equality in the previous slides. Okay? And this penalty term does not depend on BC dimension. Again, I brought up this in practice. So in practice, we use n divided by 5, right? Yeah, I'm just going to stop here and we carry on other techniques for cross-validation on Friday, so we can conclude this section with that. Any questions?